The human brain is a masterpiece of evolution, refined over millions of years to perform complex tasks with unparalleled efficiency. It consists of approximately 86 billion neurons connected by trillions of synapses, operating seamlessly to manage everything from sensory perception to decision-making. Despite its immense power, the brain operates on remarkably low energy, about 20 watts, roughly the equivalent of a dim light bulb. For scientists and engineers, the brain has long been an object of fascination and a benchmark for designing intelligent systems. Neuromorphic chips, designed to emulate the brain's structure and functionality, represent a groundbreaking step toward bridging the gap between biological intelligence and artificial systems. Neuromorphic chips are a specialized type of processor designed to replicate the neural architecture of the human brain. The term neuromorphic was first introduced by Carver Mead in the 1980s, marking the beginning of a revolutionary approach to computing. Unlike traditional processors based on the von Neumann architecture, where memory and computation are separate entities, neuromorphic chips integrate these components into a unified structure. This allows for real-time data processing, minimizing latency and significantly reducing energy consumption. Modern iterations of neuromorphic technology, such as IBM's True North and Intel's Loihi, have demonstrated the ability to handle complex tasks with an efficiency that rivals biological systems. At their core, neuromorphic chips are designed to simulate the activity of neurons and synapses. Neurons act as the brain's processing units, transmitting electrical signals, while synapses serve as connections facilitating communication between neurons. In neuromorphic chips, these functions are replicated using a combination of analog and digital circuits. Electrical impulses in the brain are mimicked by electronic signals, enabling the chip to perform highly parallelized computations. This structure allows for the processing of vast amounts of data in a manner similar to the human brain, opening doors to applications that require adaptive and intelligent behavior. One of the most promising aspects of neuromorphic chips lies in their ability to mimic the brain's learning and adaptation processes. Traditional computers operate based on predefined instructions, whereas neuromorphic systems are capable of learning from data inputs and adapting their functionality over time. This ability is particularly relevant for machine learning and artificial intelligence (AI) applications, where continuous improvement and adaptability are critical. By incorporating features like spike time-independent plasticity, a process inspired by how synapses strengthen or weaken based on activity, these chips enable machines to learn in a more human-like manner. The potential applications of neuromorphic chips are vast and transformative. In the healthcare industry, they could revolutionize the diagnosis and treatment of neurological disorders such as Alzheimer's, Parkinson's, and epilepsy. These chips could enable real-time brain monitoring, facilitating early detection of abnormalities and offering personalized treatment plans. In prosthetics, neuromorphic chips could enhance the functionality of artificial limbs, making them more responsive and intuitive by mimicking the brain's natural control mechanisms. Similarly, brain-computer interfaces could benefit from neuromorphic technology, enabling more seamless communication between humans and machines. In robotics, neuromorphic chips represent a leap forward in creating robots capable of real-time perception and decision-making. These chips enable robots to process sensory inputs, such as vision and sound, with remarkable speed and accuracy, allowing them to navigate complex environments and interact with humans more naturally. Autonomous vehicles, another critical area of application, stand to benefit from the rapid perception and decision-making capabilities of neuromorphic chips. By processing environmental data in real time, these vehicles could react faster to potential hazards, making them safer and more reliable. Energy efficiency is another significant advantage of neuromorphic chips. Modern AI systems are often criticized for their high energy demands, which pose sustainability challenges as AI adoption continues to grow. Neuromorphic chips, by contrast, are designed to operate with a fraction of the energy required by conventional processors. This makes them an ideal solution for deploying intelligent systems in resource-constrained environments, such as remote sensing devices or wearable technology. Despite their immense potential, neuromorphic chips face several challenges. One major hurdle is the complexity of their design and manufacturing. Replicating the intricate architecture of the brain in silicon requires advanced materials and fabrication techniques, which can be costly and time-intensive. Additionally, while neuromorphic chips aim to emulate the brain, our understanding of how the brain functions is still incomplete. This gap in knowledge poses limitations on how accurately these chips can replicate biological processes. Ethical considerations also come into play as neuromorphic technology advances. The potential to create machines that mimic human intelligence raises questions about the boundaries between humans and artificial systems. What happens when machines become capable of learning, adapting, and possibly even exhibiting traits resembling consciousness? These questions highlight the need for responsible innovation and regulation in the field of neuromorphic computing. Projects like Neuralink and BrainGate are pushing the boundaries of what neuromorphic chips can achieve. Neuralink, for instance, envisions a future where humans can interface directly with machines using brain implants, enabling applications ranging from enhanced cognitive abilities to treating neurological disorders. While these projects are still in their early stages, they illustrate the transformative potential of neuromorphic technology in reshaping how humans interact with technology. In the long term, neuromorphic chips could pave the way for breakthroughs in artificial general intelligence, AGI, a form of AI that rivals or exceeds human intelligence. By leveraging the brain-inspired architecture of these chips, AGI systems could achieve levels of understanding, reasoning, and creativity previously thought to be exclusive to humans. This would mark a paradigm shift in technology, with implications for every aspect of society, from education and healthcare to industry and entertainment. In conclusion, neuromorphic chips represent a bold step toward understanding and replicating the human brain's extraordinary capabilities. By combining the principles of neuroscience with cutting-edge engineering, these chips have the potential to revolutionize technology and redefine humanity's relationship with machines. As research in this field continues to advance, the line between biological and artificial intelligence will blur, opening doors to a future where technology becomes an extension of the human mind.